Okay, I think yeah. So if you have any specific questions regarding last tutorial or any questions regarding the content of the lectures uploaded by NPTEL team, you can ask here. And I think the assignment one submission date is tomorrow. Last date is tomorrow. So I will not do exactly assignment one solutions, but if you have any doubt, you can ask me. I will try to solve similar type of problems because we are not allowed to solve exactly assignment solution because then there is no point to give assignment. I mean to submit the assignment. So if you have any specific questions regarding any assignment problem, you can ask me. I will try to solve similar problems, not exactly that problem. Okay. So I'm starting now. I think my screen is visible, right? Please someone confirm me and my voice is clear to you. Please someone confirm these two are okay or not.
Yes, sir.
Okay, thank you. Okay. So someone asked that in mail in discussion forum that assignment first question and third questions right options are not there. But this is not true. There is right options. First question says let me ask the first questions. First question says they let A equals to this one is the matrix 1 2 3 minus 1 4 2 4 6 minus 2 8 1 1 1 0 2 3 6 9 minus 3 12. This is the first question. First question says that let A be the matrix and x is equals to x1 x2 all the way x5 transpose. That means basically it is asked that let x is equals to this one and y is equals to y4. Okay, yeah.
Sir, the
Um,
screen is not visible.
Screen is not visible, right?
Hello?
Screen is not visible, right?
Yes, sir.
Uh, okay, so let me just stop the sharing and share again. Now it is visible. Just 1 minute. Is it visible now?
Yeah, sir, it's visible.
Okay. So Lipsika, if you still not visible, you can join region. Maybe there may be issue from your side. Um, it is visible to you?
Yes, sir. Now it is visible.
Okay,
Yes,
okay.
sir.
Thank you.
Now it is okay.
Yeah, thank you. So if x1 is x is this and y is that, y1, y2, y4. Then question is, the system ax equals to y has a solution if there is some options relation between y2, y4, y1 and all those things. So I last class I have discussed how to solve these type of problems. Still I am, I'll try to solve here, but I will not solve this problem. So I'm erasing with this problem, but I will solve a similar problem from, which is not this one, okay? Because I am not allowed to solve this problem. So this is the question given in assignment, first question of the assignment one. So there is solution. I mean, how to do that solution, that I will just discuss, but I will not solve these questions. Sunil, you can, I mean, stop your video. Sunil Singh. Yeah. Hmm. So let me solve a problem. Uh, I'll do the similar problem. Okay, that problem says some different thing. So let me first take that problem actually. Yeah, this is the problem. This is the problem. Problem is, I think, uh, this is a problem which is I'm taking from last year. So let A be the A is a matrix. It is given like 1, -2, 0, 0 and all this way, and B is obtained from A. B is obtained from A. B is obtained from A by a finite number of elementary row operation. Okay, and let x1 equals to x1, x2, x3, x5. This is the matrix, and y equals to y and 2. Then the system has solution provided one of the conditions. So exactly same question. So I will just solve these questions, and the solution will be followed from there. Joydeep and Sunil, you can stop your video. If you are able to hear me, please stop your video. Yeah, Sunil, please. Okay, so here A is the matrix. A equals to 1, -2, 0, 0, 1, 3, -6, 2, 0, 7, -3, 6, -2, 1, -4, -2, 4, 0, 0, -2. This is the matrix A. Suppose the questions I written few minutes ago, that is the assignment one of the given assignment, first assignment of this time. So that assignment also gives some matrix like that way, and asked whether Ax equals to Y system has solution if some condition satisfying or not. So how to do that problem? So let after finite number of elementary row operation, how to do that problem? Let A mod Y x A mod Y, that is A dash. How it is written? Written is A -2, 0, 0, 1, 3, -6, 2, 0, 7, -3, 6, -2, 1, -4, -2, 4, 0, 0, -2. This is the thing. And how to write y here? Y will written this way: y1, y2, y3, y4. So here it is given that the B is a matrix obtained from A by a finite number of elementary operation. So let then system, I'm just removing this matrix because I just want to make it the previous one solution. So for now, I'm just thinking that this is not there. Okay, this is not there, and let A be the that matrix, and X is this five column vector of five elements, and Y is column vector of 4 elements. Then the system Ax equals to Y as solution when it will satisfy some condition. So let's first to do elementary row operation. Let's do elementary row operation. First, how to do elementary row operation here? First, I will take the non-zero entry of first row, that is 1 here, and then I will make all other entry below of this, the first non-zero entry. There's these 3 entry. This entry I will make this is 0. How to do that? Uh, How to do that? First, to multiply this first row by 3. So let first keep this row as it is, and then subtract it from row 2 dashed, that is new row of the matrix, that is row 2 minus 3 of row 1. So if we multiply first row by 3, then what it will be? 3 minus 6, 0, 0, 3, 3y1, right? This will be this. So if we subtract this row from this row, what will happen? So first it will be 0, and minus 6 to minus 6 it will be 0. 2 minus 0 is 2, 0 minus 0 is 0, 7 minus 3 is 4, and y2 minus 3 y1, right? Similarly, I will multiply first row by this, and I'll add this, that R2 R3 dash, that is equals to R3 plus 3R1. I'll just multiply row 1 by 3 and add with the row 3. What it will happen? Just adding with this row with this third row. Okay. So this will be, first entry will be 0. 6 minus 6 is 0. Minus 2, it will be minus 2. And 1 plus 0 is 1. Minus 4 plus 3, that will be 1 here, minus 1 here, and it will be y3 minus y3 plus 3y1. And third row, what will happen? I'll just do here. What is the process here? I'll do this operation. Just let me write it. The operation is R4 dash is equals to R4 plus 2R1. So first multiply row 1 by 2. What it will be? Element will be like this way. Okay, 2y1. So, and I'll add this with row 4. What it will happen? 0 first entry. 4 minus 4 is 0. This will be 0 again. This will be 0, and minus 2 plus 2, that will be 0, and it will be y4 plus 2y1. Okay, so now what will happen? Now just we came here. Now note that this matrix, this particular matrix, this matrix is just, this is the matrix it is given, right? This is the row reduced form, that 1 minus 2 0 0 1, the 0 0 2 0 4, and 0 0 minus 2 1 minus 1. This is the same matrix. Okay, so this is the elementary operation we have to do to get that matrix. Okay, now now question is, what we know ax equals to y system will have solution if rank of A mod y, that is this matrix, this full matrix, or number of non-zero row. I will not write rank, that term is not introduced. Number of non-zero row of A mod y or A bar y is equals to number of non-zero rows of A. So here, what is the number of non-zero row? That is 3, right? Because this is the A. This is the, I mean, after row reduction. After row reduction, non-zero row of A after row reduction, you can write. After row reduction, here is also after row reduction of A mod y after row reduction. So here what we have seen here is the number of non-zero row. Here this term is after row reduction. This means that after same number of row reduction. Okay, after same number of row reduction. So here where what we have seen, that this is the A after row reduction. So here number of non-zero row is actually 3. We can look at 3 number of non-zero row is here. So but here to get the same number of non-zero row, we must have y4 plus 2y1 equals to 0. So we must have y4 plus 2y1 equals to 0. So that means this will be the answer then. Y4 equals to minus 2y1. So this way I have to solve the questions. And you can look at this matrix. You can just look at this matrix, and also still have the solution, but this way solution will give you the exact all solution. How to solve this equation, not doing all these, okay, all these things? Because we know that whenever ax is equals to y, that means this is one equation will be something like x1 minus 2x2 plus x5 is equals to y1, and other equation will be minus 2x1. I mean, multiplying this with x1 x2 x, just for I'll write here. Suppose this one is the x1 x2 all the way, it was x5. So that means first row it multiply with this x1 x2 x row, what will give, this will give this particular equation. But now fourth row, with if we multiply fourth row with this column, what will give, this will give minus 2x1 plus 4x2 plus 4x2 minus 2x5 is equals to y2. So you can look at this way. If we multiply this first equation by minus 2, then we will get this first term. I mean, first equation, this term will be this. So right hand term will automatically equal 2y1. So we must have minus 2y1. So we must have minus 2y1 equals to y2. So this is the required condition. Okay. So this way also one can see, but this way solution, number of solution may not be the full solution we may get. So this is the first solution. This way you can solve the first questions of the assignment. So, and the third questions of the assignment. For the third questions of the assignment, you need to, no, third questions of the assignment I have solved actually similar. So now I will solve some other questions of the last year assignments. Those will help to solve you the this year questions. That is first questions number 6. That is problem number 2. Problem number 2. So this is the problem I will solve here, because there is the exactly same problem. So, but I can do it because this one is the last year. It is so what it is says, let P3x be the vector space of all set of all polynomials of degree less than or equals to 3 over r. W be the subspace of P3x consisting of elements Px equals to a0x3 plus a1x square plus a2x plus a3 equals to 0. Then Px can take the form. Now solution. Now how to solve these questions? Now I mean, Px can take the form, I mean, what to, so whether it is possible or not, a not greater than equals to 0, this is possible or not. So first option 1, this is not correct. Why this is not correct? This is not correct. Why this is not correct? Because if we take P1, let's take a vector P1x is equals to a0 x3 cube plus a1 x2 x square plus a2x plus a3, and a0 is greater than 0, right? Greater than equals to 0. But we know that okay, this is the thing which is sitting inside the px, that is w belongs to w, such that a0 is greater than equals to 0. But we know that w will be subspace of V. V is the vector space P3x, that is the vector space, that is the main vector space P3x, if C alpha, C of Px, C of P belongs to W for all P belongs to W. So now now question is that if we take P1 is something this way with A0 is greater than equals to 0, then we must have for all P belongs to and C belongs to the field, that is set of all polynomial, vector space of set of all polynomial degree less than equals to over R. That should be in real number. So in particular, for every C belongs to real number and every P belongs to W, CP should be belong to W. But here if we take a naught is greater than equals to 0 and let's take c is equals to -1, then c dot p1, what it will be, p1 at ax, that will be -1 of a naught x3 a1 x square plus a2x plus a3. So that will be minus a naught x3 plus minus a1 x square a2 minus a1 minus a3. So now minus a naught, that is less than equals to 0, right? So therefore c naught p1 need not be an element of w, need not be an element of w when w is the collection of all elements p1x is equals to a naught x cube plus a2x square plus a3x plus a4 with the condition a naught is greater than equals to 0. So that's why, that is will not be, so that will imply that w will not be a vector subspace. W will not be subspace of, w will not be a subspace of p3x. So my main point here is that if we consider W is the collection of all elements P1x equals to A naught x cube plus A1x square plus A2x plus A3 with the condition A naught greater than equals to 0, so that will not form a vector space. Why that will not form a vector space? Because if W is a subset W of a vector space P3x is said will form a vector subspace if it satisfies this condition. For all P belongs to W, P C dot P should be an element of W. But here if we consider C equals to -1 and if we take an arbitrary element like P1x equals to A naught x3 plus A1x square plus A2x plus A3, then with the condition A naught greater than equals to 0, then C1 P will be this one. But whenever A naught is greater than equals to 0, then minus A naught will be less than equals to 0. So in that case, CP1 is not an element of, therefore CP1 need not be an element of, therefore cp1 need not be an element of the set w. So whenever w is the collection of all these type of sets, so that means w is not a subspace, that is not satisfying the condition, so one is not the option. Now come to the point of second says that a2 equals to ia1, a2 equals to ia1, that is also a2 is equals to ia1 where I equals to square root of -1. But in that case, in that case Pw is not a subset, in that case W is not a subset of, in that case W is not a subspace of R, a subspace of P3x. Why this is not? Because what it is saying here is that P3x with a vector space of set of all polynomials of degree less than or equal to 3 over R. But here if we consider A2 equals to IA1, then in that case W elements with this form and A2 equals to IA1, so that means here W is saying that all the element like A naught x cube plus A1 x square plus A2 x plus A3 such that A2 is equals to IA1 where I equals to square root of -1. So this is not a subset even, is not a subset even, is not a subset of P3x, because P3x is the set of all polynomials of degree 3 or less than 3 but with coefficients over R. But if we consider A1 is equals to 1, then A2 will be minus I. Yes, A2 will be I. So in that case, any element like this form, for example, IEX, this is an element of W, but that is but this IEX is not an element of but IX is not an element of P3X. So here it is not becoming subset also. Okay, I'm taking all other entry. A1 is 1 and A2 is identity and A3 is 0. Then this will be X square plus this. This is not an element of W because this is because IX plus this element is not here also. X square plus IX does not uh, belongs to the main set where it is becoming subset. So that's why this is also not option. This is also not correct option. So now let's come to the point third one. A3 equals to A1 plus okay, let's first erase the fourth one. A3 is irrational. A3 is rational. If A3 is rational, for example, the option is that A3 is rational. Whether this is that means W equals to it is saying that collection of all all those elements A1x plus A3 such that A3 is rational number. So in that case also, this is not a subspace because W is not a subspace of P3x. Because why this is not a subspace of P3x? Let 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 root 2. Okay, this is an element of W. Here A3 is equals to that is root 2. Sorry, let's take this is 2, not 2 root 2. 2. This is just constant term or 1 can take 1. Okay, 1. And because here A3 is equals to 1 and all other entry 0, like A naught is equals to 0, which is equals to A2, which is equals to A1. The all other entries are 0. So in that case, if we multiply, if W, as we have seen the definition that W will be a subspace if it satisfies the condition that C alpha plus beta be an element of W whenever alpha and beta be an element of W. That is the only condition. First to check that W is a subspace of a vector space V if it satisfies this condition that C alpha plus beta is an element of W whenever alpha and beta are elements of W. Okay. So with that assumption, so if it fails to that condition that C alpha is an element of W, then also it will not be a vector space. So with that condition, here let's take C is equals to let C is equals to root 2. Then let P1 x equals to this. Then C dot P1 at the point x which is equals to root 2. When this is not an element of P3x. This is not an element of P3x. This is not an element of W. Because here A naught is equals to root 2 and A3 is equals to root 2 and A naught, A1, A2 all other entries are 0. But W is the collection of all those elements like this from with A3 should be rational. But here A3 is irrational, that is root 2, right? So that's why this element is not there. That's why this element is not there. So why this is not there? Because here scalar multiplication is violating. Scalar multiplication is not satisfying. So this option is also so. Therefore, W is not a vector space. Sorry, vector subspace. Subspace of P3x. So it's clear that only option it will be the subspace. So but we will check that A3. Why A3 equals to if A3 equals to A1 plus alpha square A2, then it will be. Let last option is that A3 is equals to A1 plus alpha square A2. So in that case, W it is saying that all those elements like A3x, A naught x square plus A1x, A naught x cube, A naught x cube, A1 x square plus A2 plus A2x plus sorry, yeah, plus A3 such that it is saying that A3 is equals to A1 plus alpha square A2. Okay, this is the condition. So let's take so we know that to show that we know that W will be subspace if alpha C alpha plus beta is belongs to W whenever alpha beta belongs to element of W and C be the element of the field where the subspace vector space is defined. So here we will show that this condition is satisfying. Let's take two element p1 is equals to a naught x cube, that is alpha, plus a1 x square plus a2x plus a3, and p3, this is an element of w, and p3, that means we will have, that means what we will have, a3 is equals to a1 plus alpha square a2. Alpha is a fixed number, alpha is a fixed real number, and p3 is p2 is equals to another element we are taking, p2 is equals to a naught dash x3 a1 dash x square plus a2 dash x plus a3 dash belongs to w. That means similarly it will satisfy the condition a3 dash is equals to a3 dash is equals to a1 dash plus alpha square a2 dash. So let's add these two and let C be an element from the field F, that is the real number. That is actually real number. So then C P1 plus P2. So it can be written is that C A naught plus A naught dash whole x cube plus C A1 plus A1 dash whole into x square plus uh, C A2 plus A2 dash whole into x plus C A naught A3, sorry, A3 plus a3 dash. This is the condition. So this is the last element, that is the a3 of this particular form, and this is the a1 of the this particular polynomial, and this is the a2 of this particular polynomial. Note that c a3 plus a3 dash, that is equals to c, we know that a3 is equals to a1 plus alpha square a2, a1 plus alpha square a2 plus a3 dash, that is equals to a1 dash, this one, plus alpha square a2 dash. So we can write it as a c of a1 plus, that is c a1, we can write c a1 plus a1 dash, and c a1 plus a1 dash plus alpha square can be taken common, c a2 plus a2 dash. Okay, so clearly the coefficient, this is the third coefficient, that is you can write a3, this is can be written as a1, and this is can be written as a0. So you can sorry, this is the a2, okay, this is a2, yeah, this is a2. So here particularly these are actually symbolical, I'm just writing, okay, a0, a1, a2, this is not divided, okay, this is not divided. So here we can see that a3, this is the thing here, a3 is equals to uh, a1, this is the a1 plus alpha square into a2, this is the a2. So that means, that implies that, c p1 plus p2, that is element in w, that implies w is a subspace. This, there is a similar questions of these questions, okay. So here is the only one option correct, okay. So let's do the questions number 8, another questions, that is, this is the question, just a minute, check whether these are the questions or not. Oh no, I need another question. Yes, this is also questions. But I'll do later here, okay. I'll do this one later. This one we have done. Yes, this one is the questions I will do. So this is another problem. Okay. So what is the question here? Which of the following statement is correct? So let's check one by one. So first it is said that let V be a vector space of n by n matrices over the field F. Okay, if you have not understand anything what I'm trying to say, you can ask here also. And if any questions from the content you can ask, or any questions from the assignment you can also ask. Let V be the vector space of n by n matrices over the field F. Then the solution space of a system of homogeneous linear equation may not form a vector space in F n cross 1 with respect to the standard addition and scalar multiplication. This is not correct. Why this is not correct? Let V be the vector space over the field F. Okay. First option. First one. What first one says that the solution space of a system of homogeneous equation consider a solution consider a system of homogeneous linear equation, a system of homogeneous linear equations is given by ax equals to 0. This is the in general form of homogeneous system of linear equation, where a is equals to and n by matrix, where a is an m by n matrix, and x is equals to x1 all the way xn whole to the power transpose. Then question is that whether solutions of this system forms a vector space or not. Let W be the solution space of Ax equals to 0. That means this is equals to all those x belongs to the field is F1 such that Ax is equals to 0. This is the same. So if it is, so this is obviously a subset of F n cross 1. This is a vector space over F. F is the field. So now what I have to show that W is a subspace or not. Let's take x1, let x1 and x2, these two elements are in W, and C be an element on the field F. So as x1 and x2 in W, so therefore x1 and x2 in W, so whenever as x1 is in W, so we must have ax1 is equals to 0 and ax2 is equals to 0. So now to show Cx1, now to show W is a vector space, W is a subspace of F n cross 1, we need to show that Cx1 plus x2 is again an element of W. That is what it will be. That means we have to show that a Cx1 plus x2 that is equals to 0. But we know this one. But a Cx1 plus x2, this is equals to C of ax1, because C is the scalar, C is the field element that can be transformed to left hand side without any barrier, plus ax2. But we know ax1 equals to 0, that we have seen here, and ax2 equals to 0, that we also seen here. So that means this 0 means this is 0 vector. Okay, 0 vector. So that means this implies that Cx1 plus x2, that is inside the W, for any x1 and x2 belongs to W and C belongs to F. So that means W is a vector subspace of F n cross 1. So here is the first option. Here it is asked that the homogeneous linear equation may not form a vector space of in F n cross 1 with respect to the standard addition and scalar multiplication. So that is false. Second set is that the set of all n tuples a1, a2, an in Fn such that a1 equals to 1 plus a3 form a subspace of Fn with respect to standard addition and scalar multiplication. It is saying that it will form a subspace, but our claim is that it will not form a subspace. So let's check that whether this is why this is not forming a subspace. The second option says that the set W is taken, all those element A1, A2, An belongs to F of Fn, right? Fn such that A1 equals to 1 plus A3. 1 plus A3. Okay, this is the set. Okay, so this is a similarly this is a subset of Fn cross 1. This is a subset of Fn. Now it is asked that whether this is formed as vector space or not. So let's check whether this is formed as vector space or not. Claim is that this is not a vector subspace. Claim W is not a subspace. W is not a subspace. So how to prove this? So why this is not a subspace? Let A1 dot An, this is an element, belongs to F1 W. These two elements, I'm taking two elements, A1 A2 An, B1 B2 Bn. These two elements are in W. Then what we will have? We have A3 is equal A1 is equals to, we have A1 is equals to A1 plus A3, 1 plus A3, and B1 is equals to 1 plus B3. So now what my point is that if we add these two elements A1 A2 An plus B1 B2 Bn, these two elements, this is the standard addition, so this will be A1 plus B1 comma all the way it will go An plus Bn. So this is the element, but here A1 plus B1, which is equals to 1 plus A3 plus B1 plus B3 plus 1 plus B3, that is B1, but this is equals to 2 plus A3 plus B3. Okay, so that is not equals to 1 plus A3 plus B3, because if we consider this is the new element, then what is the third element of this new element? That is A3 plus B3. This is the third component of the new element. So this is not equals to, so this will be element of W, this will be element of W if it satisfies this relation that A1 plus B1 is equals to 1 plus A3 plus B3. But this condition is not satisfying. So therefore A1 plus B1 or A2 plus B2, A3 plus B3 all the way An plus Bn, this is not an element of W. That implies W is not a subspace. But here it is claiming that W is forms a subspace. So that's why it is fails. Now this third one. The set of all n tuples are A1, A2, An in Fn such that A1 equals to 0 forms a subspace of Fn with respect to the standard addition and scalar multiplication. So subspace of Fn with respect to the standard addition and scalar multiplication. This is correct. This is correct. So how to prove that this is correct? So let's give an example. So third one is that third one says that W is equals to all those A1, A2, An belongs to Fn such that A1 is equals to 0. So this is the third one taking, right? Question number 7. N tuples A1, A2 such that A1 equals to 0 forms a subspace of this is the thing. This is a subset of Fn cross 1. Fn, right? This is subset of Fn. So now to show, so let's take two arbitrary element. Let alpha is equals to one element A1 An and beta is another element B1 all the way Bn. This is element in W. Therefore, what we will have A1 equals to 0 and B1 equals to 0, because these are the condition to be an element in W. But W is the, I am taking alpha and beta element in W. Then for any scalar C belongs to the field F, if you consider C alpha plus beta, then it will be C alpha 1 all the way C alpha n plus B1, not alpha 1, this is A1 to An A1. So B1 all the way Bn. So it will be, but A1 is 0 and B1 is 0. So second term was CA2. So this will be 0 comma CA2 all the way CAN plus no, not this one, we will add it also, CA2 plus B2 comma CA3 plus B3 all the way CAN plus BN. So this is an element in W, no doubt. So therefore W is a subspace of the vector space V. This is the V. Okay. So third one is correct. So let's check fourth one is correct or not. The set of all Hermitian matrices forms a subspace of all n cross n matrices over C. This is very important questions. It is then this is very important thing that the set of all Hermitian matrices forms a vector subspace of n cross n matrices over C with respect to the standard addition and scalar multiplication. Now here I just want to point one question here, one point. W be the let a matrix n by n, right? A be the Hermitian matrices of Hermitian matrices n by n. So A be the set of all matrices n by n over the complex number, right? Such that A transpose equals to A transpose equals to A Hermitian, it is saying, right? Okay, this is the thing where A star is equals to A bar transpose. That means conjugate transpose of the conjugate of A. Transport of the conjugate of it. I mean that is first take transpose, transpose and then make it conjugate, or first make it conjugate and then take transpose. This is the thing. So this is the set of all Hermitian matrices. Okay. So now if A equals to, and all the entries of A are complex numbers, because this is the set of all matrices or with entries, set of all n by n matrices with entries from complex number C. So if A is equals to some matrix Aij, this is an n by n matrix, then it is saying that Aij is equals Aij bar is equals to Aji. Then A transpose equals to, then if A belongs to W, then what we will have, A star equals to A. That means Aij bar is equals to Aji for all I and j, for all ij from 1 to n. So in particular, when I equals to j for all I equals to 1 to all the way n, then what we will have, Aii bar is equals to Aii. That means Aii is real, right? So that means that is all the diagonal entries of an arbitrary element A of W is real, right? This is the thing. Now all the diagonal entries of A is real. Okay. Now to W will be a subspace if it satisfies the condition that addition and scalar multiplication are closed. So at least here, to make it not a subspace, we have to show that some of them are not satisfied. So here I will show that W is not closed under scalar multiplication. Let I, that is C, that is I, this is not better to write. So okay, let's write W will be a subspace of the space of all matrices order n by n if for any alpha beta belongs to W and C belongs to complex number, subspace over, okay, this is very important, this position is very important. W will be a subspace over R if for any over C, not R. Here it is asked for over C. If for any alpha beta belongs to W and complex number C alpha plus beta should be an element of W. So in particular, C alpha should be an element of W whenever alpha is in W, alpha is in W and C is in complex number C. So let's take an element A belongs to W and C is equals to identity. Okay. So then if I consider C of A, that will be, and where A equals to Aij, that is an n by n matrix. Okay. So that is in element of W. That is an element of W. Then CA, what will happen? Element will be CA11 all the way CA1n, and it will go CAN1 all the way CANn. But here interesting fact is that CAII is equals to identity CAJJ, because this CAJJ equals to I of JJ. Okay, here I equals to actually square root of unity I am talking about. Okay, I mean square root of unity minus 1, and for all j equals to 1 to r 1 to n. So my main point here is that this is not real, but what I have said is that what we have seen is that if we consider set of all Hermitian matrices, then that means those elements, I mean those matrix A, in that case, the diagonal entries should be real. But after multiplication C here, diagonal entries is no longer real number, right? So that is diagonal entries of CA is no longer, because Aij is real number, because we are taking A be an element in W space of all Hermitian matrices. That says that Aii are real for all I equals to 1 to n. So that means Ajj is real for all j equals to 1 to r. But if we multiply C, that is nothing but the square root of minus 1. That is, I mean, complex I. So in that case, CA, the diagonal entries of CA is no longer real. Okay, so that implies CA is not an element of W when C is equals to square root of identity minus 1, that is identity. So that implies W is not a subspace. But here interesting fact is that so that proves our thing is that whether question is whether set of all Hermitian matrices forms a vector subspace of over C. This was the thing, over C with respect to the standard addition and scalar multiplication. So we have seen that this is not correct. But this is not correct. But here I just want to make one note here. Note is that here W will form a vector space over real number R with usual or standard addition and scalar multiplication. With standard addition and scalar multiplication. So this is a question which usually asked from the basic linear algebra whenever you are facing some interviews like for PhD or integrated PhD. So there is a very important question here. The set of all Hermitian matrices, that is the A star equals to A, whether that set forms a vector space. I mean, whenever W is taking as this way, I mean, here is also W is taking this way. Here is also W, or I'll better to write in red. Here is also W is taking this way. W is equals to all those matrices A in set of all n by n matrices, complex matrices, such that A star equals to A. Okay, complex entries. But this set is not from a vector space over C, but this set forms a vector space over R. Okay, so field is very important. And so that to understand these things, so this is a very good example. Okay. So this solves questions number 7. Now I'll solve. This is not questions number 7 because this is not from this time assignment, but this type of questions are there, so this will help. Okay. Now I'll solve. Someone asking whether last questions. I think last questions of the assignment, whether that is someone is seeking solution of the last questions of assignments. Okay, I mean how to solve that question someone asking. So I'll just similar questions. I'll solve a similar questions which may, I mean, I'll not able to, I'll not I'm not allowed to solve exact deep solution. So I'll solve a similar questions. That is questions number. That is some questions I'm just giving. So question that says that let V be the real vector space of all functions f from R to R. Which of the following real vector space of all functions? This is the space of all functions from R to R. Okay. Which of the following set is a subspace? These questions will help to solve the these questions will help to solve the last problem of the assignment. Of the assignment 1 of the first assignment. Okay, so this will exactly, I mean, similar way. So what are the options? Options A is that all functions that satisfy the condition f of x square is equals to f of x whole square. Option B, all functions. So in that case, asking W is equals to all those functions real number to real number such that f of x square is equals to f of x square. This is the set. All functions that satisfy the condition f of 0 is equals to f of 1. So here it is asking the set W is equals to all functions from real number to real number such that f of 0 is equals to f of 1 if this collection of functions forms a vector space or not. Option C that says that all functions such that f of minus 1 equals to 3. This says that whether W is the set like this way, all functions from real to real such that f of minus 1 equals to 3, whether this set forms a vector space or not. Last option is all f such that f of x square is equals to 3 plus f of x. That means it is asking all functions f real to real such that f of x square is equals to 3 plus f of x. So I'm just, it is very much clear from something that this will form vector space, that I will show how, and this will also not form vector space, this will not form vector space, this will not form vector space. I will show why one by one. Why I mean justification of each of the term. First it is saying that all functions from, in short, okay, it says that fx, I mean all functions of f for which it satisfies the condition f of x square is equals to fx square, whether these functions are from vector space or not. So this is not. Why this is not? Let's take f of x is equals to x square. I mean f of x is equals to f and g in w. W is equals to all functions f belongs to f from R to R. All functions f from R to R such that f of x square is equals to f of x square. This is the thing. If this is the set f and g there, and let's take c is an element in field f, that is real number here, c is a real number, then main point is that f plus g, if I want to find f plus g at x square, what it will be? F of x square which plus g of x square, right? So so this is equals to by condition f of x whole square and g of x whole square, because f and g are in x, so f of x square is equals to f of x whole square and g of x square is equals to g of x whole square, because f and g both are element of w. Okay, so gx square, but this is not need not be f plus g, that is at the point x, its whole square. For example, for example example let's take f of x is equals to x square. Okay, f of x is equals to x, f of x equals to x, and g of x is equals to also x. Then f of x is equals to x, and here it is satisfying f of x square is equals to f of x whole square. This is satisfying, right? This will satisfy. And also, and g of x is equals to g of x square is equals to this. But f plus g, that at the point x, what it gives, that gives the x plus x, right? That is equals to 2x. But f plus g at the point of x square, what it gives, it gives f of x square plus g of x square, that says x square plus x square, that is equals to 2x square. But f plus g at the point x, its whole square, what it gives, 2x whole square, that is 4x square. So that is not equals to f plus g at the point x square. So therefore w is not a subspace of subspace, that is not a subspace. Subspace of the set of space of all matrices of space of all set functions of real valued function from real to real. So that's why first one is not correct. Second one, why second one is correct? Second one is says that let's take w is equals to, this is the set f real function such that f of 0 is equals to f of 1. So whether this set forms a vector space or not. Let's take f and g, two elements from the set w. There, that implies that f of 0 is equals to f of 1 and g of 0 is equals to g of 1. And let c be a real number r. So let's consider new function cf plus g. So in that case, at the point 1, what it is gives, cf at the point 1 plus g1, that is equals to c of f at the point 0 plus g of at the point 0, that is, that can be written as cf plus g at the point 0. So that implies that cf plus g satisfies the condition to being an element of w, that means that is in w. So therefore w is a subspace. Okay, so that's why B is the correct option. And why C is not false option? All functions function f such that f is f of minus 1 equals to 3. That means this is the condition. So if we consider this type of functions C, that w is equals to all functions real to real such that f of minus 1 equals to 3. So if we take two functions f and g from w, then f of minus 1 equals to 3 and g of minus 1 equals to 3. Then f plus g at the point minus 1, what it will be, f of minus 1 plus g of minus 1, that is equals to 3 plus 3, that is equals to 6, and that is not equals to 3. Right? So that's why f plus g, that is not an element of w. So that's why w is not a subspace. Okay. Now why d is not correct action? All functions f such that f of x square equals to 3 plus fx. Similarly, d is says that w is the set. D is says that w equals to set all the functions f from real number to real number such that f of x square is equals to f of x, what is the f of x square equals to 3 plus fx. F of x square 3 plus fx. So this is the set. So similarly, let's take two element f and g here. Then f plus g at the point x square, what it will be? It will be f of x square plus g of x square. So this is equals to 3 plus fx, and this is equals to 3 plus gx. So, but this is not need not be equals to 3 plus fx plus gx or f plus gx, f plus gx, because one can construct a function such that, I mean, for example, let's take f of x square which satisfy this condition also. Let's take f of x is equals to 3 plus and something like y square is equals to 3 plus y. So y square minus y equals to 3. So y will be b plus minus root over of b square minus 4ac. Okay, this will be complex function. This function is not there actually. No function is there actually, maybe. Okay, but yeah, this is not there. So options A, C, D is not correct. So all these things will increase how to, I mean, your knowledge how to check whether a set is a subspace or not. Okay. Okay, so this will help to solve the last problem. Okay. So now I will solve one more problem from this previous assignment. Then I will go back to the week 2 content. Okay. This is not. This is not. This is done. This is done. Yeah. This is spanned by this. Then which of the following vectors is in W? Okay, so this is very interesting questions, and this type of questions is very important also. So this is a problem. What it says there, uh, okay, what it says that let W be the subspace of R to the power 4 spanned by these four vector 1 1 minus 2 1 3 0 4 minus 1 minus 1 2 5 2. Then which of the following vectors is in W? If you are asked, if you are given a vector, whether that vector is in the span of these sets or not, so then that is something different questions. Okay. That is something different questions, but here it is asked at a simultaneously. Let W be the subspace of R4 spanned by these vectors, then which of the following vectors is in W? Okay. So for how to solve this type of problems, I mean, simultaneously we have to check all the four vectors, all these four vectors. I mean, out of this, all these four vectors, which are in the span of there and which are not in the span of there. So all that we have to do in simultaneously. So for this, we consider the set W. W is the set of these vectors. So let's write this way: 1, 1, minus 2, 1, 3, 0, 4, minus 1, minus 1, 2, 5, 2, and write y1, y2, y3, y4. I mean, what is the main motivation to write this way? Suppose we have three vector alpha 1 is equals to 1, minus 1, minus 2, 1, 1, minus 1, 1, 1, minus 2, 1. This is a vector. Alpha 2 is equals to 3, 0, 4, minus 1. And alpha 3 is equals to minus 1, 2, 5, 2. This is a vector. This is three vector is there. And you are asked whether a vector y1 is equals to y1, y2, y3, y4, that is inside of the span of this or not. So that will be inside the span of this vector if y is equals to now question is then fact is that y will be in span of alpha 1, alpha 2, alpha 3 if y is equals to c alpha 1, or I'll write x1 alpha 1, x2 alpha 2, x3 alpha 3 for some x is equals to x1, x2, x3. So that means basically it is saying that y is equals to alpha 1, alpha 2, alpha 3, or this way, alpha 1, alpha 2, alpha 3, this way x1, x2, x3. So that means if I write alpha 1 as a column vector, alpha 2 as a second column vector, alpha 3 as third column vector, and it multiply with x1, x2, x3. If for some choice of x1, x2, x3 we get this one, I mean this y, then we will say that y is in the linear span of this vector. So that means basically it is saying that this full system is saying that ax is equals to y, where y is equals to this and x is equals to this. So whether does there exist any x for which this does there exist any x for which x equals to y? Okay. So now to solve these questions we have to do it for each of these four vector, right? But we will do in a single stroke. So let's see how we will do. So I'll write this a system once again, that is 1 minus 3 1 3, I think, yeah, 1 3 minus 1 1 0 2 minus 2 4 5 1 minus 1 2. Okay, this is the vector, and along with I'll write this one is in simultaneously. So let's first do a row operation. Okay, first row operation is just making all the second row, third row, and fourth row, all the entry of this here, making it 0. Okay, I mean entry in below of the first row. So for this I'll do row 2 dash is equals to row 2 minus row 1. So keep row 1 as it is. Okay, y1. So if we subtract row 1 from row 2, what will happen? 0, and 0 minus 3 minus 3. Okay, and okay, minus 3, and um, it will be 2 minus 1 minus, okay, 2 minus 1 3, and y2 minus y1. And third one, just multiply row 1 by 2, that will be 2 6 minus 2 2y1, and add with the row 3, that is row 3 dash is equals to row 3 plus 2 row 1, that will be 0 first term, and 4 plus 6 is 10, 5 minus 5 minus 2, that is 3, and y3 plus 2y1. Okay, and the third entry will be, third one is subtracting row 4 dash is equals to row 4 minus row 1, that is 0, minus 1 minus 3 is minus 4, 2 minus 1 is 3, and y4 minus y1. So this is the new matrix. Okay, so let's make that. Now what to do is just make this term 1. So to make this term 1, what we will do, we will multiply this second row by minus 3. Row 2 dash is equals to minus 1 by 3 row 2, minus 1 by 3 row 2. That will make this 1 3 minus 1 y1, and 0 1 minus 1 minus 1 by 3 y2 minus y1. Okay, and right now keep it is as it is. Okay, all the entry 0 minus 4 3 y4 minus y1. This is the thing. Now what to do here is that now make all the entry like this 3 entry 0. Okay, this is the process of row reduction. Okay, so how to make this all in entry 0? So first subtract row 1 dash is equals to row 1 minus 3 row 2. Okay, so then first entries will be, okay, then row 2 will change to 0 3 minus 3, and I am multiplying minus 3 again, so it will be y2 minus y1. Okay, this is the thing. Okay, so subtracting first row, subtracting this one from the first row, so it will be 1 0 minus 1 minus 3 2 here, and y1 minus y2 y1 minus y2 minus y1, that will be 2y1 minus y2. Okay, and 0, and keep second row as it is, 0 1 minus 1 minus 1 by 3 y2 minus y1. Now similarly I will multiply second row by 10. So what it will be? It will be 0, first term will be 0, 10 minus 10, and it will be into minus 10 by 3. Okay, and it is subtracting it from the third row, that is r3 dash is equals to r3 minus 10 r2. Okay, so what it will be? 0, 10 minus 10 will be 0. Okay, so 3 minus 10, that is 13, and it will be little complicated, but that calculation need not be do. 10 by 3 y2 minus y1. This is the thing. So this is the matrix. And third one, just multiply the second row by 4. So what will happen? That 0, 4, minus 4, and minus 4 by 3 y2 minus y1, and add it with the fourth row, that is r4 dash is equals to r4 plus 4 row 2. Okay, so 0 0 here, 3 minus 4, that is minus 1, and it will be y4 minus y1 minus 4 by 3 y2 minus y1. Okay, so keep it is as it is right now. So, and one more thing, where here I have to do one more calculation here only. Just what to do here is that multiply this fourth row, I mean replace third row by third row plus 13 times fourth row. 13 times row 4. So what will happen? All other entry will be as it is, 1 0 2 2y1 minus y2, 0 1 minus 1, this will be minus 1 by 3 y2 minus y1, and this will be 0 0 13. Okay, I am adding here, so row 3 is the replacing by this way, so this will be 0 here, because 13 times this row will be, I'll just 13 times row 4 will be 0 0 minus 13, and this particular thing will be y4 3 y4 minus 3 y1 minus 4 y2 plus 4 y1 by 3 it was, so 3 y4 plus y1 minus 4 y2 by 3, and 13 times here, multiply by 13 here. I think 13 is something abstract term is coming here. 13 is maybe not correct, just let me check once. No, 13 is not correct, I think it was 10 r3 minus 10 r2, r3 minus in r2. Okay, we can do change, we can interchange also, but yeah, that's okay, not a problem. Okay, what we can do, let's don't do this here, let's don't do this, we can keep up to this point also. From here we can also obtain the solution. That solution will be, so from here what we can say here is that, if we multiply y4 minus y1 minus 4 by 3 y2 minus y1, then this equation by 13, and this we add with this particular equation, 2y1 minus 10 by 3 y2 minus y1 is equals to 0. So we have to simplify it. And check which one of these particular symbols, this particular four equation, if you consider y1 y2 that way, so which one of these are satisfying these conditions. check which one of these options are satisfied these conditions. These conditions. So here what will happen? Only option will be first one will satisfy the condition and no other. So option will be correct option will be A and correct option will be A, that is 0, 3, 3, 3, and all other will not satisfy this condition. Will not satisfy above condition. Okay, so check it this one. Okay, so this is all for that assignment one. I don't think any other problem I can solve. Okay, so let me check one problem one can solve. Yeah, this is a problem that is very short problem. I will just do it quickly. Let's V be a vector space of all n-by-n matrices over R. Then which of the following set of matrices is a subspace of V? I will here do as fast as it is possible. So for all A such that A square, first option is not correct. Similarly, if we consider A plus A and B, I mean similarly W is equals to all those matrices here, real matrices, okay, all those matrices of R such that A square is equals to A plus identity. So if we consider A plus A and B, two matrices are there, A and B in W, then A plus B whole square, that will be A plus B into A plus B, that will be A square plus AB plus BA plus B square, but A square is equals to A plus identity, okay, and B A square equals to A plus identity and B square is equals to B plus identity, okay, so plus AB plus BA is there, okay, so then this will not form vector space. I have to give an example. For example, if we consider A equals to, okay, let's consider A equals to, it is saying that A square equals to A plus identity, right? So that means x square minus x plus 1 equals to 0. So that means x is equals to plus minus 1 root under 8. Okay, okay. This is the that two vector. Okay, so that means if we consider here if we consider A is equals to WA. Okay, W is the cubic root of unity. W identity. Here W is the cube root of unity. Cubic root of unity, that is W is equals to minus B plus minus root under B square minus 4AC. Okay, this was x cube minus x plus 1, x square minus 1 plus x equals to minus plus 1 root under B square minus 4AC by 2 I say, that is equals to minus 7. Okay, this will be minus 3. Okay, this is the actually by 2. W is equals to 1 plus this. Okay, so we know that W square is equals to 1 minus root under minus 2 by 2 this, and then B is equals to W square identity, then A and B both are element in W, but A plus B, that is equals to W plus W square, which is equals to identity, that is equals to minus 1, because we know that W plus W square plus 1 is equals to 0. Okay, so this is identity that is not contained in W. Okay, that is not contained in W. Why that is not contained in W? Because I3, in case of I3, minus I3, this square is not equals to minus I3 plus I3. That is not satisfying because minus I3 square is itself I3, so that is not equals to I3 plus I3. Okay, so that's why first option is incorrect. Second option is the a cube equals to a. That is also not correct. Similarly, one can consider this is also not correct. Why this is not correct? W is equals to all A belongs to n by n matrices of order such that a cube equals to a, then A is not a matrix, then a cube equals to a, then question is that then W is not a subspace. W is not a subspace. For example, one can consider here A equals to identity, right? And B is equals to like ident B equals to can be considered as 1 0 0 W. If we consider W square and W key is 1, so W square will not be there. So I cube, I can be considered, right? Then B cube is equals to 1 0 0 I cube, but I cube equals to I square into I, but I square equals to minus I, minus 1. So that is not also correct. Okay, B is not also correct. So what can be taken? W, if we consider W cube is 1, W square, W cube is 1, 0. We can take this one, right? A is this and B is this. Then A, B both are. So A is equals to, I'm taking right now, A equals to 1 0 0 1 and B equals to this. Then A plus B, that will be 2 0 0 1, right? But A plus B whole cube, that is equals to 8 0 0 1, right? That is not equals to A. A is 2 0 0 1, right? So that's why W is not a subspace. Secondly, A is such that AB equals to B minus BA for some fixed vector B. Then, so here is that third option says that W is equals to all those matrix n by n such that AB is equals to minus BA for some fixed vector matrix n by n order. So this is because if we consider A1, A2 in W and C is an scalar, that is a real number. I think real number it is considering. All those matrix are real number. Then CA1 plus A2, this will be in W if and only if CA1 plus A2, if it's multiplied with B by this way, then CA1 plus A2 will be an element of the say set W. But CA1 plus A2 whole into B, this is equals to CA1B plus A2B. But we know that A1 and A2 are element of W. That implies A1B is equals to minus BA and minus BA1 and A2B is equals to minus BA2. So if we replace this one, it will be C into BA1 plus minus C into BA2 and that will give minus B CA1 plus A2. So that gives CA1 plus A2 is an element of W. That gives W is a subspace. Okay. And now last one, all such A for which A is invertible. This will form a subspace of V or not, right? Which of the following set of matrices is a subspace of this is not a subspace because if A and B are invertible, then A W is equals to option D is that W is equals to all those matrix, real matrix n by S such that A is invertible. Okay, so this set will not form a vector space. Why? For example, if we consider A is equals to identity 2 by 2, for example, then it is invertible. Okay, because this is invertible. And if we consider A2 is equals to minus identity, that is also invertible. But A1 plus A2, that is equals to 0, that is not invertible, as 0 matrix invertible. Okay, 0 matrix is not invertible. So that's why, I mean A1, A2, I mean, so D is not a vector space. So therefore W is not a vector space. Therefore W is not a vector space. Okay. So these four conditions. So this is not correct actually. W is invertible, whether this is vector space or not, this is not correct. This is not vector space. Okay. So this is the full content of the week one actually basically. Now in week two, what is it is teaching? There is the 3-4 facts that I'll just quickly recall in 5 minutes, in 10 minutes. So there is the notion of linear span. That is the linear span of a let S be a set with some vector alpha 1, alpha 2, alpha n, or it can take any arbitrary finite number of vectors. Note that S is a set, S be a set or subset. Let's take, okay, let V be a vector space, L is subset of B, S is in subspace, S is in B in subset of V, then linear span of S denoted by Ls given by over a field, let V be a vector space over a field F and S be a subset of V, then linear span of S, that is Ls, is given by, that is summation of Ci alpha I equals to 1 to n, where n is a positive integer natural number n, and alpha I are element from S and Ci are element from F. So here what is I am saying, all finite linear combination of the elements from the set S. That is all finite linear combination of linear combination of elements from F. So here finite is very important term. Why finite is very important term? For example, if we are taking S is a finite set, for example, um, set of all polynomials with degree less than equals to 3. Okay, so in that case, finite polynomials are there. Okay, I mean I can take only finite number of linear combination of a finite number of elements, that is, let's set of all polynomials of degree 3, that is, or I'm taking, okay, for example, forget about this thing. Let V be the set of all V be the space of all polynomials, okay, over R, okay. So I mean coefficients are coming from R, that is over R means coefficients are coming from R, and let S be the set 1 x square, then Ls will be all Ci x to the power I equals to 1 to 2, I equals to 0 to 2, such that Ci are real number. This is all, right? So then this will be subspace of all polynomials, of degree 2 or less than 2, degree 2 or less than 2, okay. So my point is that if you consider S is 1x square, then take the linear combination of the set S, then what we will get? We will get the subspace of set of all linear polynomials of degree less than or less than degree 2 or less than 2, right? This is the thing. But if we take, let's take S is equals to all, okay, like this way, S is equals to x to the power n such that n is even. N is even. I am taking right this way. S is something x to the power n, n is even. Then this is a subset of the vector space V. V is the space of all polynomials. So here if we consider LS, what it will happen? I equals to 1, 0 to mm, some finite m such that Ci x to the power 2i, where m is a finite, m is a integer. Okay, so x to the power 2i, writing x to the power 2i, that means this is the all the coefficient, all the power will be even number. So that means it will be the space of all matrices or space of all polynomials with degree, with elements at degrees, I mean even degree, something like that. Okay, not even degree, that term will not be correct, but I mean elements are something linear combination of even polynomials, even degree polynomials. Okay, this is the thing. So here point is that here the note that S is infinite. S is an infinite set. Infinite set here. But linear combination is taking as finite number of elements. When the linear combination is taking, when the combination is considering only finite number of finite linear only finite combination is considering. Okay, so main point here is that even the set, if set is finite, then when we are taking linear combination, that is finite linear combination. But if set is infinite, then we can't take this m is infinity. Even the set is infinite, linear combination will be taken as always finite number of elements. I mean linear combination will be taken of finite number, finite linear combination will be taken always. Okay, so this is the main reason. Okay, so now, I mean, this point someone, I mean, may miss. I mean, miss. So that's why I'm saying. So linear combination is take like considering this way. I'll just check if there is any questions regarding linear combination. So if there is, then I'll solve that one. Okay, there is nothing. Okay, second is that linear space is there, and second is that linear dependence, linear independence. I will not consider go there. And third is that the fact of basis, dimension, number of linearly independent vectors in a basis, or basis is always contains number of linearly independent vectors. Now, and third is that the row space. Okay, row space I will consider a little bit, and I will solve the problem. Let A be an m by n matrices. Just before, let A be A is an m by n matrices. Okay, A be an m by n matrices matrix. Okay, and A is equals to, I am writing A ij. This is m by n. So that means this will be like A11 all the way A1n, and AM1 all the way AMN. Okay. Now if we consider alpha I is equals to AI1 all the way AIN for all I equals to 1, 2 all the way m. That means alpha 1 is the first row, alpha 2 is the second row, and in this way alpha m will be the last row. Okay, alpha m will be the last row. So this is the case. Then alpha is our, then alpha is our row of uh, rows of A. Now one can write A in this form, then alpha 1, alpha 2, all the way alpha m. One can write this way. Okay. So let's take P. Let P be equals to Pij. This is an K by M order matrix. Okay. Then consider B a new matrix that is equals to P by P multiplied it. Right. So that means I can write this way P11 all the way P1 M, and it will go pk1 all the way pkn. This is the matrix P, and alpha A is written by this way, right? A. So this multiplication will be actually this will be summation of Pij alpha I j equals to 1 to m, and this is the first one. So all the way last one will be pkj alpha j equals to 1 to m. So main point here is that interesting fact is that rows of, so therefore rows of B are actually linear combination of rows of A. Now row space of A, what is row space of A? That is this is I am talking in some for other purposes, but what is row space, that I'll first talk. The row space, let A be a matrix, let A be a matrix of order m by n, then the subspace, then the space generated by the all rows, generated by rows of A, is called row space. What is that I want to mean here is that let's take A be a matrix. Okay, it has row. For example, A is a matrix, n by n matrix. It has m number of row. Now, if we consider alpha 1, alpha 2, alpha m as element, they are element, right? They are element in vector. They are element in f n. There n is the, if we consider real, that is there is the element in Rn, right? They are element in Rn. So they are element in Rn, right? So now if we consider S is the this set, and consider the linear span of S, then this will be some scalar times of alpha I equals to 1 to m. Okay, this is the all elements C belongs to real number. So this will form a vector space. This LS, space of all linear combination of the elements alpha 1, alpha 2, alpha m. This will form a vector space, and that vector space is called the row space of the matrix A, right? So how it is becoming? Let's take A is a matrix, and considering each row as a vector in appropriate subspace or vector space, that is Rn or C to the power Cn or something like that, and then consider linear combination of all elements of that set, then that will go form a vector space, and that vector space is called the space of row space. Okay, so here what we are, so this is the row space. So what we are getting here is that, but interesting fact here is that if we multiply the matrix A by a matrix P that is of order K by M, then what we are getting, the new matrix B and the rows of that new matrix are actually linear combination of the rows of A. So therefore row space of, therefore I mean rows of B are actually linear combination of rows of A. But if we consider rows of B, then what will happen? That will be the linear combination of rows of B. But rows of B are actually linear combination of rows of A. So therefore, row space of B actually, row space of B is a subspace of row space of A. Why this is happening? As row space of B is linear combination, is linear span rows of B, but each row of B is a linear combination rows of A. Okay, so 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 that's why rows of B actually linear combination of rows of A. I mean, basically, if I consider B1 is a row of B, then this is equals to some scalar multiple of row of A, I equals to 1 to M. Then if you consider row space, then what will element? Element will be something like summation of Ci dashed or some new constant like um, Pi I equals to 1 to K. So then what will happen? I just again replace I equals to 1 to N and each Bi by Ci alpha equals to Cj alpha j equals to 1 to M. Then I will get a new element like whatever the coefficient is there and then alpha j. So that is basically I will get that will basically I will get linear combination of rows of A. So that's why row space of B is a linear subspace of row space of A. So now question arises when the reverse is possible not. I mean, suppose we have B is equals to PA, and we are saying that in that case B is actually row space of B actually linear combination of subspace of the row space of A. So now in other round we are asking when the row space of A actually subspace of row space of B. So that will happen if P is invertible. If P is invertible, if P is an n by n invertible, if P is an m by n invertible matrix, then B equals to PA, that implies that A equals to P inverse B. Okay, so therefore row space of A is actually, therefore by a similar argument you give that one can say row space of A is a subspace of row space of B, and in that case row space of A and B are called equivalent. When the Q is P is invertible, in that case row space of A and row space of B actually equivalent, are equivalent. That means what my point here is that if row space of, I mean, in that case, row space of A can be obtained from the by a finite linear combination of rows of B, and row space of B can be obtained by a, I mean, row space by from row space of A. So therefore, row space of A and row space of B are actually are obtained from each other. So that's why row space of A and row space of B are equivalent. So, and if that is the case, so for the same reason, for this reason, if we consider let A x equals to, if we as we have, okay, that just something we have seen in the last tutorial. We have seen in the last tutorial that row reduction echelon matrix is obtained, is nothing but matrix is obtained just by just by multiplying a suitable invertible matrix. So that is, my point is that is, consider Ax is equals to y be a system of linear equation. Okay, system of linear equation, and after row reduction, let R be the row reduced echelon form of A, then R actually will be obtained from P for an invertible matrix P. For a suitable invertible matrix P, right? For a suitable invertible matrix P, if we multiply P by A, P from the left hand side of A, then we'll get the row reduced matrix. Now, um, now, so that is the reason. So for the above reason, for the above argument regarding row space of a matrix, rows rows non-zero rows of R form a basis of A. What I'm here, my point is that we have seen that if B equals to PA for some invertible matrix P, then row space of B and row space of R actually equivalent. That means row space of A can be obtained by a finite number of linear combination of elements of row space of B, and other row space of B can be obtained finite number of linear combination of row space of A. So, but here what I am trying to say here is that if let's take P is an invertible matrix and R equals to PA, okay. So in that case, sorry, let A be a matrix, and in that case, by a row reduction echelon form, we get R. So that means R is actually equivalent to saying that R equals to PA for some suitable matrix P, invertible matrix P. Therefore, row space of R and row space of A are equivalent. So therefore, not therefore, row space of R and row space of R equivalent. Row space of R are same with the row space of R is same with the row space of R is same with the row space of A. Row space of A. So what is the what we can say, I mean, what advantage of this thing? Advantage of this thing, row R being row reduced echelon form, each non-zero row are linearly independent. Being in row reduced echelon form, non-zero rows are linearly independent. Non-zero rows of R, actually, non-zero rows of R are linearly independent. As well as they as well as non-zero rows of R spans row space of A. Therefore, non-zero rows of R forms a basis of A. So this is the main point. Okay. So this is the point I want to make sure. Okay, so on the basis of this, if I get any problem, I will try to solve that problem. Just one second. Row 1, row 2, row 3, and row 4 of our matrix is represent which of the following elements belong to the row space of A. Huh. So I'll do one problem which will take nearly 3 minutes, 4 minutes maybe. Not this one. Yes, this one. So this problem. So here, how to solve these questions? On the basis of this, on this whatever I have said, on the basis of this problem is consider the matrix given in question 1. So that matrix, consider the matrix A, where A is equals to I'm just writing that matrix is needed. Matrix is 1 minus 1 0 1 2. Other is 2 minus 2 2 4 6. This is minus 3 3 0 minus 2 minus 6 1 minus 1 minus 2 1 0. So this is the A, this is the matrix A. Okay, let me just check once I'm written correctly. 1 minus 1 0 1 2 2 minus 2 2 4 6 minus 3 3 0 minus 2 minus 6 1 minus 1 minus 2 1 0. So here what is the question? Consider the matrix A given below. Which of the following set can be considered as a basis of the row space of A? Okay. So what we have seen here last is that if we do the row reduction process, then the row reduced echelon form of the matrix will be the basis of the spacing. So let's do the row reduction process. So here, how to do first here is that first what we will do that row 2 minus row 2 dash is equals to row 2 minus 2 row 1. Okay. So what will get? I'll get the row 1 is as it is. Okay. I'll get row 1 as it is 1 0 1 2. Okay, let's do it on the left hand side little because 1 minus 1 0 1 2 and multiply row 1 by 2, that will be 2 minus 2 0 2 4. So and if we subtract it from the row 2, what will happen? This and this will be 0 minus 2 0. 2 minus 0 is 2, 4 minus 2 is 2, 6 minus 4 is 2. And now multiplying row 1 by 3 and add with the row 3. With the, so what is then multiplying by row 1 by 3, it will be minus 3 0 3 6. And if we add it with the row 3, then what will happen? 0 0 0 3 and minus 2, right? Yeah, 3 minus 2, that will be 1 minus 6 and plus 6 0. Okay, okay. Just let me check. 1 minus 1 0 1 2, 1 minus 1 0 1 2. So 3 minus 3 0 3 6, and the last one I'll just subtract it from the row 4. Okay, so that means I will write row 4 dash is equals to row 4 minus row 1. So what will happen? This will happen 0 minus 1 0 minus 2 0 is minus 2, 1 minus 1 is 0, 0 minus 2 is minus 2. So this is the thing. Okay, now if we do row reduction process again, um, so first let's keep it like this. So 1 minus 1 0 1 2. So you can look at the first entries that already came. So we have to find the second entry. So we have to based on the second and third entry. So and next is what I have to do. I'll just multiply row 2 dash is equals to 1 by 2 R1. So R2. So that will be 0 0 1 1 1, and this will be 0 0 0 1 0 0, and I will multiply row 1 dash row 4 dash is equals to row 4 minus 1 by 2 by row 4. Okay, sorry, minus 1 by 2 by row 4. So this will be 0 0 1 0 1. This is the matrix. Now if we subtract row 3, sorry, row 4 dash is equals to row 4 minus row 2, then what will happen? Everything will be there. 1 2 0 0 minus 1 1 0 0 1 1 1 0, row 4 minus row 2, right? Row 4 minus row 2, it will be as it is. So 0 0 0, it will be this minus 1 minus 1 0, right? So now if we just do one thing, that add row 4 dash is equals to row 4 plus row 3, what will happen? 1 1 minus 1 0 1 2 0 0 1 1 1, and it will be 0 0 0 1 0 0 0 0 0 0. Also I do one more thing, that row 2 dash is equals to row 2 minus row 4, so then it will be row 3, so it will be 0 here also. So this is the row reduced form. Okay, this is row reduced echelon form. Okay, so therefore the matrices, therefore the vector 1, this vector, this three row vector will form the basis of the row space of A, right? So this is the what I have tried to say before. Therefore 1 minus 1 0 1 2, this is one vector. 0 0 1 0 1, this is second vector, and 0 0 0 1 0, this is third vector. This is a basis of the row space of A, of the row space of A. So this is how basis is constructed. So let's see which option is the correct option here. So this is the correct option, then all other option will be incorrect, because there is only one option is possible. So this from the row space of, this from the basis of the row space of, because this set is linearly independent, as well as this is row equivalent to the space of row space of A. So therefore this will form linear subspace. This will form the basis of the row space of A. So I will stop here. If any question is there, please ask it now. Okay, or you can ask later also. Anything you have not understand from this tutorial session, or anything from the um, anything from the what I'll say, from the lectures. Okay, I just want to know one more thing. Is there any network issue from my side? I mean, is it feels to you? I think I feeling that maybe sometimes there is a network issue. Okay, if any questions, please ask. Otherwise, I will stop in 1 minute.